Thanks. Okay, so I will talk a bit about audiovisual applications of Supershape polygons and complementary N-gon waves. Supershape polygons, maybe you have encountered them already, maybe not. We will see. So at first, I will give a short overview about the talk and the contents of the talk. It's first we'll talk a bit about curves, just like general definitions and polygonal chains, and then there will be a bit more audio focused part, which is on sonification and audification, what this actually means, and then there will be a short introduction to Supershape polygons and what does interpolation mean for frequency and timbre in music and sound. And then we will have a look at an audiovisual phenomenon where the same shape can have a different sound. And there will be a short introduction to complementary N-gon waves, and then complementary N-gon waves applied, or the algorithm applied to Supershape polygons. Of course, there are effects of discretization on audiovisuals and actually what that means for representing a shape and or a geometry in sound and in visuals. And then there is composing with supershapes is something that hasn't been covered yet, so I couldn't find anything about it. So there will be a bit about timbre polyphony and scales. Timbre polyphony was already introduced in 2021 when I worked together with Johan. So at the Symmetry conference. Then there will be a short introduction to currently existing Supershape audio software, and we'll continue with audiovisual geometry database, which is also another application or interface, how to compose with Supershapes. And then will be a bit of discussion on graphical user interface, software interface to Supershapes and how they could be arranged to create something like music out of these geometries. And last but not least, I always like to point towards the connection between geometry, audiovisual, and perception. So, okay, so I will start with a short definition on curves. So Doyle Hankins gives a description on curves or a definition in his book Lectures on the Philosophy of Mathematics. And he defines it as a curve in effect describes a way of traveling along a certain path. One is at position ct at time t. The curve therefore begins at point c0. It travels along the curve as time progresses, and it terminates at the point c1. And the next point is quite crucial for audiovisual applications. Curves are allowed to change speed, cross themselves, and even to move backwards on the same path, retracing the route. The images below show different curves, like the common sine and cosine waves, a circle, a Gielis transformation at the center, a Lissajous figure on an oscilloscope, and a supershape visualized on an oscilloscope. So a polygonal chain is a curve consisting of line segments that connect a sequence of vertices. Examples that we can see here are an open polygonal chain and a closed polygonal chain. A closed polygonal chain, of course, also is reminiscent of a polygon. Two polygonal chains can be used to construct a closed polygonal chain, and vice versa. Two polygonal chains can be derived from a closed polygonal chain, which is the polygon again. The images below show examples on an oscilloscope created with complementary N-gon waves. So the triangle on the left is a visualization of these two waveforms, actually what is commonly known as triangle wave and an N-gon wave. So they both could be seen as a polygonal chain that construct a closed polygonal chain, or actually a polygon. So now from music, when data is used to create music with it, just in general, there is a distinction between sonification and audification. And sonification is a bit a more broader term, where it means that the amplitude values of a sine wave, for example, they can map to like anything. They could be controllers for amplitudes, they could be controllers or parameters for the timbre or the duration and so on. So here is an example where the amplitude values of a sine wave are approximately mapped to the notes of a musical scale. That is the regular 12-tone equal temperament scale. So the equation is just at the bottom. So I will play the example. I hope you can hear the example. Could you hear the example?
Yes, a bit, a few tones.
Okay, it is very short.
Yeah.
Example. Okay, so it's just simply the piano notes. They just follow the sine wave, and it's kind of mapped to the sine wave is mapped onto this logarithmic scale of which is actually based on the 12th root of 2. So I will move on with the next slide. Audification, in contrast, is a very direct way of sonification of musical or any kind of data, or geometrical data, or could be any data. What's being done there is we directly write the samples of the data into the sound buffer of a sound card, and we can play it back via speakers. So the output of the sound card can then also be connected to an oscilloscope for visualization, which is indicated by this small oscilloscope on the right. So here it is just the example shows a digitized sine wave in 4 bits. And you might be quite familiar with the sound. It just sounds like a sine wave. Sorry, we'll play the sound. Yep. So we'll move after this introduction into a bit aspects of data turned into sound. We can have a look at Supershape polygons. Supershape polygons could be understood as when the lines of the polygon actually connect points on a supershape. Just quite similar how the points on a circle can be connected by lines to create like polygons, regular or irregular polygons. Yep, so the equations here just show the Gielis transformation, which you might all be familiar with, and then just how the interpolation is being done for, or could be done with how these lines could be calculated. Yeah, maybe you could say like this. You might be familiar with these equations. I'm not going too much into the details. This is just like the interpolation equation is equation 8, and the slope is equation 7, where we take the difference of a delta y and a delta over delta x. So, yep. Now, different types of interpolation have an effect in audio on timbre and also frequency. So they result in different waveforms. So that's why here we focus a bit on what types of interpolation can actually be used. So because it's not that it's just a general way of interpolation that could be applied to all these polygons, and then we would have the same sound. So it's actually quite recognizable that these produce different sounds. It's kind of obvious, but it's I think it's quite interesting because I couldn't find that being explored too much in relation with geometry. So there are some attempts, but yeah, so it's just a close look at interpolation. So if we use the same divisor T for delta x and delta y, the delta x and delta y are being the distance between the points on the x and y axis of a shape or a polygon, then the shape is always reconstructed, which can be shown on an oscilloscope also, or in a digital visualization. So we could, for example, use the Euclidean distance between points for the interpolation. So the slope would then be delta x over t, and t would be just like the Euclidean distance between both of the x and y points on the x and y axis. Sorry. We could also use a constant divisor, for instance, inside of a unit circle, which then gives a very periodic waveform. So this is an interesting equation because you can kind of tune the shape very easily with this equation. So that would be equations 13 and 14, where the delta set value has to be introduced as an additional dimension to mathematically compute these or calculate the divisor t in this case to create a unit distance. So that's kind of interesting because it's adding this additional dimension. So it kind of the shape becomes kind of three-dimensional. And we could also have like a periodically changing divisor that would be like, for instance, a sinusoidal function or whatever. It can even change randomly. And it will still reconstruct the original shape, actually, the waveforms were derived from. It could also, of course, approximate infinity. So it might be, yeah. So we could also use different divisors for delta x and delta y. This is something we will look into the next slides when I talk a bit about N-gon waves and complementary N-gon waves. So here is an example using a random interpolation. On the left, we see a polygon, just a simple square that is visualized with supershapes. It's a supershape, so we have a supershape wave, so we have a steady angular frequency. Then there is another one which uses very few samples on the lines of the square, so it's like the velocity changes per line. Yep, so that will still reconstruct the original polygon on the oscilloscope. Then we can also use more points as samples, and still to use random distances between the points on the lines. So we get an effect which is quite similar to phase noise. So the lines become a bit, say like, less exact or look less exact. Nevertheless, they will still reconstruct the shape on the oscilloscope. So this leads to what I'm calling an audiovisual phenomenon, which can also actually be observed with regular Lissajous figures, but it's actually that the same shape can have a different sound depending on the waveforms it is used to construct, or the waveforms are used to construct the shape, and which kind of brings us back to the introduction sentence by Joel David Hampkins, where it is said that actually the point on the line is free to move in every direction and at every speed. So in these examples on the right, we see a sinusoidal approach where we have like the shape is constructed by a sinusoidal function. It's like amplitude or radius modulation. And then the next that we have on which for example, might use Euclidean distance, where a point travels along the perimeter of a shape with some sort of unit or steady speed, which is actually then results in a combination of frequency and amplitude modulation. And the one at the bottom is an example of an N-gon wave, which actually also introduces discontinuities, or can introduce discontinuities, which is more like an up and down and left-right movement of a point along a shape. So from here, we can just now continue with complementary N-gon waves. So the N-gon waves actually, as maybe some might have already wondered whether they actually require additional waves to actually reconstruct the wave because of the discontinuities and so on and so on. So it's actually 4 waveforms can be derived with using N-gon waves from a shape. So first I might want to describe a bit what N-gon waves are. N-gon waves are waveforms that retain the angles of the polygon they were derived from, which can be seen on the example in the middle. We can see that, for instance, if we use a hexagon and then create an N-gon wave from the hexagon, we get a hexagonal wave looking like wave, so we can fit hexagons in on, say, like below and above the wave. So yeah, and similarly, we can do this with squares to produce even the regular triangle waves, or even the regular sine, sorry, not sine wave, but sawtooth wave. The sine wave is actually not included. Instead, a circle-like wave is produced with N-gon waves. So now, to reconstruct the polygon, the waveforms they were derived from, you would need an additional wave, so which I'm calling the complementary wave. It's a very angular wave with orthogonal angles. Examples can be seen at the bottom. So if we derive our waveforms along the x-axis of the original shape, so we will move along the x-axis of the shape, and we will need another waveform along the y-axis that will be used to reconstruct the original polygon. And we can do this also on the y-axis, in moving the point or our sampling point along the y-axis of the shape. It's a bit like having a train passing by, or like slit scan cameras work. So, well, in the end, we have actually 4 waveforms. So it's a kind of quadraphonic oscillator derived from a 2-dimensional shape. And all these waveforms, they can be combined individually, which is shown in the matrix on the right. So in the matrix on the right, some shapes look similar, but actually they all have a different sound. That's quite unique to N-gon waves. They also change the frequency, so, and the timbre, so in a different way than other waveforms do, which is maybe kind of obvious, but it's not that obvious from the matrix, because the shapes look the same, but it will have a bit, maybe a different pitch, maybe the timbre is a bit different, and so on. But they all derived from the same polygon. So now we can also apply the algorithm that is used to create N-gon waves, or the mathematics is used to create N-gon waves, to supershapes. So here is a comparison of supershapes, a circle at the left and some sort of super ellipse at the center, and then again the square to the right, of supershape waveforms, which are a bit the thicker waves, or the one with a bit heavy width below the shapes, and the one with the less thick lines are the N-gon waves actually derived from the supershape. So we can see that we can also reconstruct the actual square wave-like waveform, but also with, I say, like more like instead of less angles, if we use the super ellipse, it will have maybe perhaps a bit less aliasing that instead of very angular waveforms would have. So that's quite interesting to explore. But here's just an example how they can actually, how N-gon waves actually, the algorithm can be applied to supershapes. And we will also use an example where the supershapes, polygons, or supershapes, complementary N-gon waves of supershapes are created. Now we can also clearly see that the complementary angular waves at the bottom, they are very angular because of the left and right or up and down movements of the sampling. And if we put them all together, for instance, like in a musical composition where one shape would be followed by another, there might be discontinuities introduced because of the angular waves, which can introduce clicks in sound, which at some point can be desirable, and at some points we might not want to have clicks. So this is something I'm going to talk a bit later on also. It's something to consider when you create a musical instrument that uses geometric waveforms in general. This is actually not only a characteristic of N-gon waves, so we also we'll see later that this has an effect on other types of waveforms. So of course we can also create N-gon waves of supershape polygons. Here just a few examples where the polygons inside of a supershape are recreated as N-gon waves, actually, or complementary N-gon waves. So there is an effect in audiovisuals which is caused by actually the digitization of a shape, which means the number of samples or the sampling rate being used for scanning or recording a shape, and the frequency of the waveform that is reproducing this shape actually affects the shape of the polygons and the waveforms themselves. So the higher the frequency actually, and the lower the sampling rate, the more the characteristics of a shape are reduced or even skipped, which is illustrated here with where we can see that when we use less samples, or like for instance supershape as on the left, we can see how certain peaks and spikes of the shapes are actually skipped. So I was interested in this, and when for instance Euclidean distance was used to reconstruct the shape, so the small red dots on the green supershapes, there should be an approximation to the Euclidean distance actually. So it's more like an approximation in this case here. But there is an effect which is not only cannot only be seen as in these examples here, but it can also be heard, of course. So and composing with supershapes is there are some let's say special characteristics of supershapes. One is the timbral polyphony, which we introduced at the Symmetry conference. That is actually the waveforms themselves, they have a kind of musical characteristics, so they can sound like multiple instruments at the same time. It's a bit like in Fourier, you would say you have different sinusoidals added together to create the timbre of an instrument. So, but it's very interesting because we can use this actually as a tool for composition. So the timbral polyphony itself from the shapes can be used for compositions. Then there are also musical scales. There are that are particular to supershapes. They actually related to the turning number and or the complete period of a wave. So it's a bit of I say it depends on what point of perspective you take on the shapes, whether you want to use the turning number to define the frequency of a wave, or you want to use the complete period of a wave to determine to define its frequency. So the turning number is very much related to how we perceive the sine wave or sinusoidals. So that's a very obvious choice, actually. But the more irregular the shape becomes, the more also the actual period of a wave is perceived. So here are just a few examples that illustrate the timbral polyphony. Yep. I mean, images show this timbral polyphony. Then there are also already some softwares which use the super formula. For instance, there is the Super LFO or the Super Formula Special 2.3. One is for a VCV rack, which is some sort of virtual modular synthesizer. It's free and open source. And the other one is for the Reactor software, which is also a kind of virtual modular synthesizer. There are also other softwares that already use the super formula to create sound with. So it seems that it's already being used, but I don't know of too many actually examples of music that really use them. And of course, they are not using Supershape polygons, so this appears to be something quite new. And in addition, there are no manuals. Usually they just give the parameters, but there is no introduction on how to compose with super formula oscillators. So they're just being used a bit more like an effect, especially with an LFO, where you can then modulate, for instance, the amplitude or the frequency of another waveform, like which is very often the more regular sine or triangle or square wave or the sawtooth wave. One I also have to note that there are also softwares that use like polygonal waveforms or polygons. For instance, Dinny's noise or the Polygogo, also the harmonic pattern function, which is a tool or actually a thesis by Putnam, but it's not being released yet. Then there is also Ossi Studio, which is dedicated to oscilloscope music. There they use Blender and to use the Blender shapes, the shapes created in Blender, and for visualizations on oscilloscopes. So we have created an audiovisual Supershape library together with Johan. So, which is a library of recorded waveforms of supershapes. The special requirement for this, or the application for this, could be for people who actually do not want to use the Supershape oscillators themselves. It's quite common that like libraries for samples exist. So that's why this was very interesting. Also, we can create like very, very low frequency waveforms, which will be very long, which is usually something difficult to reproduce in real-time oscillators. It can work as well if it's computed, if the waveform is computed while it is also being replayed, actually with a little bit of time difference between them. So we compute first and then we display the waveform a little bit later. So yeah, but a sampling library is something very useful, I think. And it's already been used by composer Rexleigh Bunyard, part of our collaboration. And she has created a first composition, or actually she already had composed a piece of music which she has translated into super shapes. So she used the library to use the super shape sounds, and it's called Pond Filter. So I'll play the example. Not sure whether you can hear it.
No, we cannot.
And the start is kind of a bit silent, perhaps. Can you hear it now?
No, and I also switched the Zoom back to music for musicians, so I cannot.
Okay. Hmm.
Maybe.
Okay, I check the audio settings.
So maybe I can play it from my computer and then.
Yep.
Do you hear it?
I can hear it, yes. I think it's with now.
Sorry?
I think it's in a loop. Okay.
Okay, I'll tune it down a bit. Okay, good. Good.
Okay.
So this
Thank
is
you.
a world premiere, huh? So.
Yeah.
Please, Dominic.
Okay. So now, of course, thinking about how could musicians interact with supershapes to create music with, especially compositions. We are, or especially me, I'm thinking of how could that actually be made accessible to regular musicians? So because it's a very geometric thing for musicians, sometimes it can be a bit abstract, maybe to turn that into music. So one thing we're exploring at the moment is whether a torus-like or a Möbius strip-like interface could be used. Because actually, if we look at the supershape, which is replayed in time as a visualization of two waveforms played back in time, we get sort of a helix. So we can actually use a torus, a helical torus. So then some questions that appear are how actually can one shape be morphed into another? Because of course because it's a continuous order formula, the supershape formula, we can also have like polygons that are like transcendent or rational numbers. So the question is, how could they be actually morphed into one another? A very common one is crossfade, where just one shape is morphed into another by addition and subtraction. So one shape is added and the other is subtracted, which then produces some interesting intermediary shapes. But theoretically, we could also change the shape parameters, which is quite interesting. For instance, there could be a phase rotation, which means like changing the phase, which results in the rotation of a shape, which is indicated by the image on top left, which is also very Möbius strip-like. I think Johan and Ilio have also looked into this quite a bit. So that would be more like a musical application here. Then we could also use like a torus-like shape for placing shapes on the torus. and for instance saying like, okay, I want one shape at this position and one shape at that position, and then the software would actually calculate fades between the parameters. There might be the issue with, because if, for instance, if we use a polygon with 4 vertices and one with 3 vertices, in between there will be all sorts of transcendental and irrational numbers, which potentially produce infinitely long waveforms. Of course, we cannot play these waveforms back, or so they would have to be limited or faded in and faded out and so on. So these are interesting challenges for actually creating a graphical user interface for composing with supershapes, because otherwise you would just like twist the knob, and then you would know, okay, if I change this parameter, then I get that visual and so on. So perhaps this might be a bit less intuitive than if you could just like select a shape, maybe then twist the parameters and then add it to the ring. You could also create a loop where the sound is repeated and so on and so on. It's just something to be explored. So there are no results there yet, but it's hopefully there might be something in this direction being developed sooner or later.
Yeah.
So what I also think is very interesting here is also a slide I always like to show in audiovisual presentations or presentations on audiovisuals, that we actually have some kind of a geometry underneath, which is turned into visual. We are very used to visualize geometric shapes, but it can also be turned into audio. And what that actually means for perception, does it mean the audio is also perceived as a sort of shape? And we might not be trained to perceive a certain sound as a certain shape. So that's a very interesting relationship between geometry, audio, and visual and perception. So finally, I will play a short example of a visualization, actually audio visualization. I'm not sure whether you can hear the sound. So again, so yep. So I'll just play, and maybe afterwards, Johan maybe would have to try to play the sound. So the frequency is very low at the beginning, and then it gets more and more audible, or should theoretically, but maybe you can see the shapes. It is actually playing back a musical scale. So
I'm playing it now.
you're playing it? Okay. So I should maybe stop mine so you could play
No,
it.
it's fine. It's fine. It's just getting the idea. Just getting the idea. Huh?
Yeah, it's actually what's interesting with this example is that we can hear a musical scale, and then if the shape is changed, we kind of can notice the timbral polyphony, how it actually changes the perception of the pitch, or maybe a fundamental pitch of a sound. So that's a very interesting relation actually between the example and yeah, being shown. But that was actually more or less it. So thank you for watching this presentation. Yeah, that was mainly it.